This lesson is about higher order partial differentiation. At the end of this lesson, you must be able to determine higher order derivatives using partial differentiation. The higher order partials, or we have the higher order partial derivatives. Recall that if we have y, a function of x, it is possible to determine higher order ordinary derivatives of the function y. In like manner, if we are given z, function of x and y, it is also possible to determine higher order derivatives. Now, what we had been working on previously in terms of this symbol, which is the partial derivative of f with respect to x, and the partial derivative of f with respect to y are called the first order partial derivatives. And since these are also functions of x and y, then it is possible for us to differentiate either one of these, again with respect to x or with respect to y, defining a second order or the second order partial derivatives of the function. And if we will do it this way, then we may encounter one of four possible partial or second order partial derivatives as follows. We have the second partial derivative of f with respect to x, which is obtained by differentiating partially with respect to x, the first partial derivative of f with respect to x. Okay, so this one can also be denoted by the symbol f sub xx. The second partial derivative of f with respect to y is obtained by differentiating partially with respect to y the first partial derivative of f with respect to y, denoted also by f sub yy. Here we're differentiating the partial derivative of f with respect to x with respect to y. And in doing so, we define the second partial derivative of f with respect first to x, followed by with respect to y. Or if you will be using a notation of the form, then it is given as f sub xy. So you do first the partial derivative with respect to x, followed by that of y. But if you are using the symbol, then you go and work on the derivative from right to left. So do first the partial derivative with respect to x, and then differentiate the result with respect to y. So in the case of the second partial derivative of f with respect to xy, this is obtained by differentiating with respect to x the first partial derivative of f with respect to y, or you denote this as f sub yx. Now take the case of the last two forms here. These are referred to as mixed second order partial derivatives, or simply the mixed second partials, because the variable of differentiation that was used here are different, unlike the first two that we are differentiating partially with respect to the same variable. So to illustrate what we have just mentioned, here we are given the function f of xyz defined equal to x cubed, y to the fifth, z to the seventh, plus xy squared plus y cubed times z. We are asked for f sub xxy. This would mean third partial derivative of f twice with respect to x and then with respect to y. So following the order of differentiation as indicated by the subscript, we do first partial derivative of f with respect to x, the result we differentiate with respect to y, and then the second order derivative will be differentiated again, but now with respect to y, to obtain the third order derivative. So if we will proceed, for f sub xxy, we do the following. First is to obtain f sub x, or the partial derivative of f with respect to x, differentiating this particular expression with respect to x while holding y and z constant. So for the first term, the partial derivative with respect to x would just be given by 3x squared coming from the derivative of x cubed multiplied by y to the fifth z to the 7, which is considered constant. Now, as the second term, the partial derivative of xy squared with respect to x would just be equal to y squared. And as for the third term, the partial derivative would be 0 because we are considering y and z constants. Now, having obtained the first partial derivative of f with respect to x, we now work on the second partial derivative of x, the second partial, derivative of f twice with respect to x. So this result of the first partial derivative of f with respect to x, we differentiate again with respect to x to obtain 6x y to the fifth z to the 7. Now this is second partial derivative of f twice with respect to x. Now if the third derivative is the one required, and it is the third derivative of f, then differentiating f twice partially with respect to x and then followed by y, then this is obtained by differentiating the second partial derivative of f twice with respect to x with respect to the variable y. So in here, x and z are considered constants. So we'll have 6x z to the 7 as a constant factor, and then we multiply that with the derivative of y to the fifth with respect to y, which is equal to 5y to the fourth power. So that based on this, the third order partial derivative of f done twice with respect to x, then with respect to y would be given by 30x y to the fourth z to the 7. Okay, recall that if you are given a function f of xy, then there will be 4 distinct second partial derivatives. However, the mixed second order partial derivatives of this particular function are said to be equal. That is, f of xy is equal to f sub yx, meaning the second order partial derivative of f first with respect to x followed by the partial derivative with respect to y would equal the second partial derivative of f done first with respect to y, then followed by a partial derivative with respect to x. In this particular problem, we are asked to confirm that the mixed second order partial derivatives of f are equal given the function f of xy equal to 4x squared minus 8xy to the fourth plus 7y to the fifth minus 3. So we proceed as follows. We first determine the partial derivative of f with respect to x, differentiating this with respect to x while holding y constant, and the result would just be an 8x minus 8y to the fourth. Now, if the same function is differentiated partially with respect to y, then we will be treating x constant. Hence, the partial derivative with respect to y would be equal to a negative 32xy cubed coming from this term plus 35y to the fourth out of this term. Now, from there, knowing that this is the first partial derivative of f with respect to x, you now can differentiate this result partially with respect to y to obtain the second partial derivative of f with respect to xy. So we differentiate with respect to y, treating x constant, and the derivative or the partial derivative would just be equal to negative 32y cubed. Now, as to the result of the first partial derivative of f with respect to y, when you differentiate this result again with respect to x, you define the second partial derivative of f with respect to yx. Okay? So when you differentiate partially with respect to x, you will be treating y constant, and therefore the derivative of the first term or the partial derivative of the first term would just be equal to negative 32y cubed, and the partial derivative of the second term with respect to x would be 0. So with this, having the second partial derivative of f with respect to xy given by negative 32y cubed, and the second partial derivative of f with respect to yx also given by negative 30 to y to the third power, or y cubed, then we conclude that the second mixed partial derivatives of the function f are said to be equal. Okay, so summarizing what we have today, that given a multivariable function, it is possible to differentiate the partial derivative, again, partially with respect to either of the variables now involved, to be able to work out what we call higher order partial derivatives of the function. And that if we are given a function in two variables, f of x, y, then the second order mixed partial derivatives are said to be equal.